don't have problem about these questions, now we're going to talk about symmetry in physics. Okay, it's quite an advanced topic in modern physics, but I hope it can help you to unify many seemingly different issues into the same kind of consideration. Okay, so in physics there is an important theorem called Noether's theorem. Okay, Noether's theorem is discovered by a German mathematician. Okay, in fact, he's a mathematician, Amy Noether. Okay, she lives in this time. Okay, about 100 years ago. Okay, he discovered the Noether theorem, which says that any conservation law, in fact, comes from the symmetry of the system, some kind of symmetry of the system. So here, for example, we have the conservation of the energy, total energy. Okay, it's the result of the time translation symmetry. What is a time translation symmetry? It's kind of like if I change the origin point of the time, we wouldn't change the system. For example, we say in fact we use this factor for many problems. We solve the problem like any kind of projectile motion. We say this is our initial time, so t equals to 0 here. And this is our final time, right? T final. But if we say, if we don't want to use this as our initial time, we can think about some initial time here. So here t will not be 0, maybe t equals to 2 seconds. And then our t final is just our original t final plus 2 seconds, right? If we change our origin of the motion, go back to like some here, and we add 2 seconds if it's 2 seconds before. For every time here, we wouldn't change any physics here, right? It's just like we change the original point for the time axis. Okay, it's nothing wrong here. So this is kind of time translation symmetry. Similarly, the spatial translation symmetry, that's even easier to understand. If you have some, let's say, one-dimensional motion, it starts from here and stops here. I say this is x not equals to 0. This is x final. But if I move original here to here, then I say x naught is 2 meters, it's not 0. And then this add 2 meters wouldn't change anything, right? So this kind of things, trivial mathematical redefining numbers, in fact, they called symmetry. So the spatial translation symmetry will give rise to the linear momentum conservation. And the rotational symmetry, it just says that when you rotate, okay, if this is the rotation axis, and the motion, you have some rotation here, so every direction is symmetric with each other. This particular direction, this particular direction, there's no difference. They are symmetric with each other. So this is the spatial rotational symmetry. Okay, it will give rise to angular momentum conservation. Okay, so here we would not be able to explain why a symmetry corresponds to a conservation law. That requires a lot of mathematical knowledge. But we find that it's always true. Any kind of symmetry will introduce some conservation law. In fact, in the quantum mechanics, because you don't have, in most cases, you will not be able to solve the Schrodinger equation. It's very difficult. So we have to rely on the conservation law. How can we use our conservation law? We try to identify what kind of symmetry exists existing in that system, and then we write down the corresponding conservation law. Okay, and there are many more conservation law in the quantum mechanics, like the charge conservation. Okay, That's also corresponding to some kind of symmetry. So that's important. And by the way, for the this woman, Amy Norton, okay, during her age, female will not be able to, cannot do be appointed as a professor. Okay, at that time, all the professors are male. But since she is a very good mathematician, the university, I forgot which university, calling the university, would like her to teach math class. So what happened is that he actually taught math class at the university. But all her class is registered in another mathematician's name, Hilbert. Okay. Hilbert is another very famous mathematician. Like in quantum mechanics, we are going to study the Hilbert space. It's named after him. So all the classes is officially registered and Hilbert's name, under Hilbert's name, but she is the one who actually taught those classes. Okay, so for the symmetry, it's more important than just to introduce some kind of conservation law. If you go further to study the complicated phenomena like the material, the symmetry and symmetry breaking plays a very important role there. Okay. You know that we have different states or different phases for the matter. Like you have solid, liquid, and gaseous state, right? For the, let's say, water. For water, you have ice, steam, and the liquid water. These different states actually correspond to the symmetry and symmetry breaking. So the ice or crystalline solid, they are less symmetrical state compared with water, with liquid or gaseous states. So you can think about a typical crystal. You have some lattice like this. Right? Okay, I think you've probably heard about the crystalline lattice. So you have some atom on this side, but not in. But for the gas, if you have container, this gas can be in any position. They are moving randomly in the container, right? So this one we see that it's more symmetrical than this one. Okay? More symmetrical means that there is no direction preference. All the directions are the same. There is no location preference. All the locations are the same in the container, right? In terms of the atom occupation, because these atoms can occupy any place they are moving, and any direction will be the same. So it preserves both the rotational symmetry and the translational symmetry. But for this one, it's less symmetrical than that. Because direction, now you can see the direction, there are some direction is different with others. Like the diagonal direction will be different with this direction, right? Okay, you have a square, so the diagonal direction is different with a square perpendicular to the surface, right? And for the location, also different. This location is different with this location, right? You have an atom here, but you don't have atom here. So it breaks the translational symmetry. So solid is a less symmetrical state compared with the gas. In another word, maybe easier to understand, symmetrical state, we call it disordered state. And symmetric breaking state is ordered state. So this one is disordered state, the gas. And solid, crystalline solid is ordered state. This is maybe, this makes more sense for you, right? This is ordered, this is disordered. So different states is actually correspond to different degree of water. Okay, so gas is very disordered system. Solid is a crystalline solid is very ordered stage. The non-crystalline solid or liquids, there are something between them. Okay, so that's symmetry, breaking edge. Okay, and symmetry in the material formation. And if you study the material science, I don't know if you have, you're going to study material science you have all kinds of these lattice, okay, all kinds of configurations. This is square, or you have hexagon, or other, okay, like these things. All kinds of formations, so they have different symmetry. Okay. Another thing I'd like to notice that usually when you have solid crystal, we say that it breaks the translational symmetry. Most various symmetries break this translational symmetry. If you break the rotational symmetry, you are going to get magnet. Okay. So all kinds of phenomena or material in our world, they can be classified in terms of the symmetry. But to explain the magnet may be too complicated. So just mention. Okay, let's stop here.